hi everyone. So we continue chapter 4. The next topic is empirical cumulative distribution function. So this is one of the most important concepts in this chapter. So basically we are thinking about the cumulative distribution function. That is the function of x, that is probability of random variable x is less than lowercase x. So it's a little bit hard to see, but this is lowercase x, this is lowercase x. So probability that some random variable, for example, normal random variable, is less than x, that is defined as capital F of x. For example, capital F of 0 for standard normal distribution, that is probability of x is less than 0. So that is the area on the left-hand side of the x is equal to 0, so 0.5 for standard normal distribution. So capital F. So capital F is just usually the smooth function. It's given mathematically. But think about estimating this function f by data sets. So suppose we observed x sub 1 to x sub n observations. Then we can estimate this capital F of x by this f hat of x. So this is number of observations. This is defined by the number of observations with xi is less than x over n. So if, for example, 7 out of 10 observations are less than 2, then basically f hat of 2 is 7 over 10, so 0.7. So this is approximately the same as f of x, right? So this x is random. So of course, we have some fluctuation, so some randomness. But basically, if we have a large number of observations, capital F of x is pretty close to true f of x. So this is called the empirical CDF because this is an estimate for CDF. So this is one example. Suppose we have 4 observations, just a very small example. So 4 observations and we sort this in increasing order. Then f hat of x is equal to 0 if x is less than -1. For example, if x is -2, no observation is less than -2. So 0 out of 4, so 0 over 4, so this is 0. If x is between -1 and positive 0.1, for example, if x is equal to negative 0.5, one observation out of 4 observations is less than negative 0.5, so 1 over 4. So f hat of x is 1/4. And we continue. And if x is larger than 1.3, all observations, for example, x is equal to 2, then all observations are less than 2, so f hat of x is 1. Yeah, and this is another example. So we generate the 10 standard normal random variables here, standard normal random numbers, and so we just count the length of x. Actually, n is 10. Then to make the empirical plot, actually empirical CDF is, start with 0 for small x, then 1/10, 2/10, and 3/10, 4/10, and finally it becomes the 1, 9/10, and 1. So that can be written in this way. At first, if we generate random numbers, then after that we sort this number, and then we put this plot, and the y-axis is the 1 to n over n. So 1 over n, actually it should start with 0, but the 0, 1 over n, 2 over n, and so on. So here n is 10, actually. So then we can make this histogram. Actually, this start with 0. So actually, we need to add this part, this one more step, and one more horizontal line here. But just it is a little bit complicated. If you see the next page, actually we can fix that problem, but it's just very detailed. unimportant details, so just we leave it as is, then this function can make it. Okay, so maybe we can implement it in R now. If we generate 10 random numbers, okay, so this is negative 1.53, negative 1.4 up to 0.86, then okay, n is actually length of x, but this should be just 10. And then we plot empirical CDF. Then we can get this. Actually, this changes the time to time. So this is the one we get. But if we define x again, and plot, it will be slightly different one. And this graph approaches to standard normal, the CDF, if n gets larger. We try that. So we make this maybe a little larger, 20. Then we have, still it's zigzag curve, but it's a little smoother than the case that n is equal to 10. So if we make n is equal to 100, then okay, so this looks like almost a CDF. You can see the plot x. Okay, so maybe we think about maybe a from maybe negative 3 to 3, so maybe negative 30 to 30 times 0.1. So A is this sequence from negative 3 to positive 3. And we think about the cumulative distribution function, that is probability of norm. So the P of norm A, we define this as B. Then plot and B, and maybe this should be a smooth curve, so maybe we can make it as a line graph. Okay. Then this is CDF of normal distribution, but if n is large, actually we have seen that this curve is pretty close to the CDF, so it's a good estimate for cumulative distribution function.